So far, what we have looked at is when we put charges next to the conductor, either outside it or inside it in a cavity, what would happen? The total charge of the conductor still remained zero. The conductor, if I looked at it globally, was still neutral, except at different surfaces of the conductor became rich in electrons and the other surfaces had more positive charges. Now what we want to understand is what would happen if I take a conductor, and let's just put a cavity too, and I release excess charge into it. Where would that charge go and sit? You can think of just connecting this conductor to a battery, and by connecting it to the battery, the charge of the battery will come and be released into this conductor. And once I have released this charge in the conductor, how would the charge be distributed? And how would the electric fields be created? Let's start with a thought experiment. I have some arbitrary shaped conductor, and let's assume it is completely solid. And what I do is somehow I connect it to a battery for a short time, or I rub a glass rod on silk and then touch the glass rod to the surface of the conductor. I have released charge Q on it. Let me ask you, what do you think would happen? Would this charge just go and sit somewhere inside like that? Or would the charge be distributed over the volume? Or would the charge be uniformly distributed over the surface? So this is charge will stay together as one point, or distribute in a volume, or uniformly distribute over a surface. Or if you don't like any of these, none of the above. None of these options. Well, this choice is ridiculously wrong. You can consider this charge to be consisting of many small pieces of positive charges. These positive charges hate each other, they repel each other. Why would they sit at one point when they have free path on the conductor to go anywhere they want? They absolutely hate each other. They would repel each other. Why would they just sit together at one point when conductor is allowing them a free path to go, path without resistance, to go anywhere? You can also prove that these two are completely wrong. How? just apply Gaussian surface. If the charge is sitting inside the conductor, inside the volume of the conductor, then this cannot be true. We know that electric field inside a conductor is zero, so the flux has to be zero, so Q net has to be zero also. If the charge is sitting inside the volume of the conductor, Gauss law cannot be true, and we know Gauss law is always true. So any charge we release will go to the outside surface. So any charge released into a conductor will always go to the outermost surface. Even if I have a conductor with a cavity, and instead of releasing the charge outside, I connected the battery to the inside part of the cavity, and I release Q inside, that Q is going to travel to the outermost boundary, and ultimately that Q is going to go and sit on the outside surface. This charge will go and try to distribute itself to the furthermost surface it can go to, which is the outside surface. Please keep that in mind. Charge in a conductor can never be distributed in a volume, and a released charge in a conductor, wherever you release it, will ultimately go and sit on the outside surface. The next question which arises is, how would it sit on the surface? Is it uniform or non-uniform? How can we answer that question? Whether the charge would sit uniformly on the outside surface or whether it would sit non-uniformly on the outside surface. Let's try to answer that question. And to answer that question, we will do another thought experiment. And we will consider a very simple case and see what happens in that simple case, and try to extend the thinking from that simple case. So what I have is a sphere of radius r1, and I release charge q on that sphere. When I release charge q, this charge goes and sits on the outside surface, and because the sphere is nice and uniform, symmetrical shape, there's no reason why charge should be distributed non-symmetrically. The charge would be distributed uniformly. Sitting next, but very far away, so that they don't the electric fields of each other are zeros around them, or approaching zero around them. There is another sphere, conducting sphere of radius r2, and I've just assumed r2 is greater than r1. Now what I do is, so they are very far away from each other. And that's just for our calculation, ease of calculation purposes. Now what I do is I take a very thin piece of wire or a conductor and I connect them together. So this is another conductor, very thin. So we can assume there is no charge within that conductor, but it allows a path for charges to move. What would happen to this charge Q? Would this charge Q just stay here? Absolutely not. This charge sees a new path and a new place where it can distribute itself. Again, remember, all these positives hate each other. They don't want to be sitting next to each other. They want to go as far away as possible from each other. And then some of these charges will see, hey, there is a path and there may be something. I can probably go further away from them, from the other charges, if I go on that path. So charge is going to redistribute. I do not know exactly how much charge is going to be present on one or the other till we do the calculations. So let's assume that there is charge Q1 here and Q2 here on this R1 and radius R2. The total charge still has to remain Q. It is basically this Q, part of this Q, which decided to come and sit on the other sphere. So the charge is still conserved. Q1 plus Q2 should still be equal to Q. Right? Again, remember, we can only redistribute charges. We can't create it or destroy it. So this charge Q distributed itself as Q1 on one sphere and Q2 on the other sphere. How long would this distribution continue? When would these charges be happy? When both these spheres are at the same potential. Remember, this has become a single conducting position. So the potential which is here on V1 and the potential which is here on V2, those potentials have to be equal. Once these potentials have become equal, then charge has no electric forces happening on it for them to move any further. So the potential has to become equal for both the conductors. This, again, these two are very far apart, and this is where we are using that approximation. The potential of the conductor, this is a sphere with a charge Q1, potential on the surface of a sphere with a charge Q1, symmetrically distributed, is simply KQ1, the total charge divided by the radius of the sphere. So V1 is simply KQ1 by R1 and V2 is KQ2 by R2. We have two unknowns, Q1 and Q2. We do not know what these two values are. These are the two values we are trying to calculate. And now we have two equations. We have an equation that the potential has to be equal, which is an equation in Q1 and Q2, and the total charge has to be equal to Q, the charge we started with. So let us use these two equations and try to calculate what a charge Q1 and Q2 would look like. So it is telling me charge Q1 would be R1 by R2 Q2. And if you want, you can calculate Q1 plus Q2 is Q. If we substitute these values, we would get, let's substitute Q1 here, we would get 1 plus R1 R2. Q2 is equal to Q. Q2 is R2 by R1 plus R2Q, and Q1 must be R1 by R1 plus R2Q. If we look at the ratio of the charges, that ratio is going to be R1 by R2, as we can see directly from this term. Since R1 is greater than R2, it is telling you Q1 is greater than Q2. The larger sphere, I think we had the opposite way. R2 was greater than R1 in our diagram. So Q2 would be greater than Q1. The larger sphere would have more charge, total charge. The larger the sphere is, that would have more total charge. However, what would happen to charge density? Charge density ρ1 would be Q1 divided by the surface area, and ρ2 would be Q2 divided by surface area, and we are assuming R2 is greater than R1. If we look at the charge density ρ1, ρ2, just divide these two equations, we would get Q1 by Q2 and R2 square R1 square. Q1 by Q2 we had said was R1 by R2. So when we look at these terms, we get ρ1 by ρ2 is R2 by R1. We had a smaller sphere and a larger sphere. The total charge which is present here versus the charge which is present on the other sphere, when we connected them together, Q1 was less than Q2, but when I look at the charge density which is present here, charge density ρ1 is greater than ρ2. Yes, the total charge here is less, but the charge is a lot closer together as opposed to the other sphere. Smaller the radius, higher the charge density. That's what we observe here. Right? So smaller the radius we get, higher the charge density. Let's say we want to, I'm choosing an arbitrary shape and I'm just arbitrarily choosing a heart. Heart muscles are decently conductive. And I have released a charge Q onto this. How would the charge go and sit? Well, we can approximate this as some spheres. And when I have sharp points, I'll have to put a sphere of very, very small radius. When I have these large areas, I can put larger spheres. So instead of having the shape like that, I can break that into small spheres, try to approximate it by summing it up with spheres. And when the radius of curvature is very, very large, then I can fit in a large sphere there. When I get to these sharp points, I'll have to put a very, very small sphere there. And what we just observed, smaller the radius, higher the charge density, it tells me that there must be higher charge density here compared to here. Any place where I have these sharp points, I would have a higher charge density. So first thing to notice is charge is distributing only based on the outside surface shape. And how would charge distribute? Charge would distribute to make the surface same potential or equipotential. That's how charge would distribute itself. And to make this surface equipotential, any place where I have a sharp points, that's where you would start seeing a lot higher charge density. And as we will later see with boundary conditions, the electric field outside is dependent upon the charge density. The strength of the electric field outside and the charge density are going to be related to each other. We will see that in the next section. So we would have a much stronger electric field at these sharp points compared to the weaker, to the lesser or larger radius of curvature points. This is exactly the same reason why, if you have seen lightning rods are very, very sharp points. Why? They can concentrate the electric field right at those points, and then if there is a lightning, they can take that charge and ground it to the earth. Compared to what is surrounding it, electric field at those points suddenly become very, very strong. So when lightning happens, it takes that path where the electric field is high. And thus we can protect our buildings and our infrastructure by using these conductors with sharp points. If you are playing golf in a lightning and a thunderstorm hits, it is in your best interest to leave your clubs away, right? So the lesson we have is charge released on the conductors will spread to the outermost surface and distribute itself based on the surface shape such that the complete surface or the complete conductor, in fact, not only just the surface, the complete surface slash conductor is at the same potential. It will have higher charge density where you have sharper points. It will not be uniform. That was the question we had started with. Wherever you have a sharper points, it would have higher charge density. And that is also that is not only true for the charge released into the conductor, this is also true for what would happen when you have charge in a cavity. Let me consider that quickly. Let's say I have a charge Q which is present, and I have a conductor which is a heart shape inside, but outside is a nice sphere. So all this is a conductor. Well, as we have seen, this is charge which is fixed inside a cavity. There would be minus Q charge present here, and again it has to be equipotential, so the charge density in this region is going to be larger than the charge density here, and similarly here too. Anywhere you get these sharp points, the charge density is going to be larger. This minus Q is coming from the outside plus Q. That charge doesn't see that it has a heart inside it. That charge plus Q is only seeing the outside surface. It's trying to make the outside surface equipotential. The outside surface is looking very symmetrical. Every point is roughly the same, has the same radius of curvature. So that charge Q, which is present on the outside surface, that would be uniform. Right? Keep that in mind. Inside here, things can change around. I could have another cavity. Let's say this is two spherical shell with a cavity inside, but I place the charge Q asymmetrically inside. In that case, again, I would have more a negative charge to where this Q is present, because it will be attracted more towards this Q. The total charge here would be minus Q. The charge outside would be plus Q, but it does not see what is happening inside. It does not worry about this asymmetry. Again, remember, electric field has already gone to 0. That charge which is sitting outside will sit uniformly because the surface outside is a nice symmetrical surface. So you will get uniform charge density outside. So we have covered now how charges would travel inside the conductor and where they would sit if you release them into the conductor. They will always go to the outside surface, and then the charge density would depend upon the surface shape.